Well, all right, everyone. Thank you for joining the August webinar. We have presenter Bob Lee and Richard Stockton, applications engineers for RF Venue. Want to thank everyone for your time today and joining on this webinar. It's kind of a new one for us. We tend to talk more about antennas, distros, and RF, but this is going to break down the entire anatomy of a wireless audio system. So a little bit different, a little bit more educational, a little bit more technical, all really good things for people who want to know. So I want to thank Bob, thank Richard. Richard's going to be answering any questions you may have as we go. So go ahead and ask anything in the questions and answers section. You guys have also submitted a truckload of questions. We're only going to be able to get to so many of them today. I think we have about 6 picked, but we'll try and answer you directly. Our team will be fielding those questions for you directly afterwards. So really appreciate that. Those questions, really good questions. Also, we're going to be sending you a survey at the end of this to see how we did, and we'll also send you the recording of the webinar once that's processed. So without further ado, Bob, please take it away.
Right. Hi. Thanks, everyone. Thanks for joining us. I'm Bob Lee. I'm an applications engineer and trainer with RF Venue. I'm joined by my fellow application engineer, Richard Stockton. I'm based in Connecticut. Richard is based in Arizona. The company is headquartered in Massachusetts. So we have the country kind of well spanned here. We're going to be talking about the anatomy of wireless audio systems, specifically wireless mic and in-ear monitor systems. So we're not going to go heavily into details or strategies. This is mostly an overview of how these systems work, because it's a good way to understand, you know, it gives you an understanding that can help you, set up your systems properly and troubleshoot when problems arise. Because we find that sometimes people, even seasoned veterans, are a little bit mystified by the boxes like distros and combiners, and they sometimes get them confused and stuff like that. And it just um, if we get this clearer in your mind, this will help you. It'll help us as well. So let's get started. Why do we use wireless audio? There's several reasons. You replace something as simple as a cable with something that's not a cable. It's bound to be a little bit complicated. But wireless mics, let's start with wireless mics. They give us mobility. So, yeah, we need that sometimes. Whether, it's a singer on a stage or um, a lecturer, a professor, maybe also actors. That's an important use for wireless mics. We can't have actors and dancers moving about the stage tethered by cables. It might be kind of amusing to see, but we don't want that in an actual production. Imagine Bono with U2, doing his rock star parkour thing. Wireless mic gives him a lot more freedom to move about and climb around on the speakers and stuff like that than he used to have with a long cable. Um, so let's see, what else does it give us? Invisibility. Yeah, I mentioned theater. There's also film and TV production. Some shots you just can't use a boom mic on. Boom mics give you a great natural pickup of sound, but you can't have them in the shot. So sound departments will put, wireless mic body pack transmitters and small lavs hidden somewhere on the actors to pick up their dialogue. And so another use in film and TV production is that on the boom mics themselves, more and more operators are using a plug-on transmitter so that they eliminate the cable between the boom mic and the sound card. And that's especially important these days because, you know, uh, productions are like a lot more fast paced than they used to be. Sometimes they do a bunch of takes in one location, they have to pick up quickly and move on to the next location and shoot some more takes. So the boom mic operator needs to have that, you know, mobility and, not have that connection to the sound card. It's a lot quicker that way. There's also, here it is, convenience. Some events, like a speech or a presentation, sometimes it's just easier to put a wireless mic on a lectern than it is to lay down a cable. Or, just give a maybe a TED talk, give them a headset and a body pack transmitter, good to go. And it just simplifies things to go wireless. In-ear monitors, they give us better hearing because the musicians are getting a direct feed to their ears of the monitor mixes. Reduce stage volume. That's a big thing because you don't have, if you don't have wedge monitors, blasting on the stage, it's going to be a lot quieter on the stage, and that can really help things. And that gives us less bleed into the mics as well. And also mobility, because it's really useful for the musicians to be able to walk around and not be locked in front of a stage wedge. So these are all really good points to have for wireless audio. It justifies the expense and complexity of replacing a cable with an RF link. So, I mean, look at what we have with a wired mic. We just have a cable going to the mixer input. That's really simple, and it's relatively inexpensive to do that. Now, if we remove that cable and we substitute it with a wireless mic system, it gets more expensive and it gets more complex. Here, because the mic has to go into a little UHF FM transmitter inside the mic body, and that sends radio waves out to the UHF FM receiver, and then that goes into the mixer input. So, like I said, it's more complex and more expensive, but sometimes it's necessary. So remember I mentioned mobility. Wireless mics and in-ear monitors operate on simple concepts, on similar concepts, I should say. The main difference is that with wireless mics, the mic and transmitter are mobile, they can move around, and the receiving system is fixed or stationary. And with in-ear monitors, it's the other way around. The transmitting antenna is stationary, and the receivers are mobile. So this means we have to take a little different approach to either one. So either way, we still rely on maintaining a reliable RF link between the fixed and mobile elements of the system. So this RF link, first we use frequency modulated radio signals, or FM. FM is highly immune to noise. Not totally, but the signal can be processed in a way that eliminates almost all of the noise. Now, in this top part of this animation, we're seeing the audio signal, the representation of the audio signal, and how it would modulate an AM system. We don't use AM with wireless audio because it's susceptible to noise. Because anything that affects the envelope of this waveform is going to come out in the audio. We use FM, shown here on the bottom. The audio signal directly modulates the frequency of the carrier signal. Okay, second, we're using UHF frequencies, typically in the 470 to 608 megahertz range for North America, 470 to 698 megahertz for much of Europe and a lot of other places in the world. And there are some other frequency ranges that vary from country to country. The third thing to know is we use very low power, usually in the 10 to 50 milliwatt range. So you think of how little 1 watt of power actually is. Now imagine a 100th of a watt of power, or a 20th of a watt of power. We're talking about, this is really low power. This is flea power. So we got to make that work. Fourth thing, we're usually sharing the spectrum with TV broadcasters and maybe some other services. So these are all things that we have to encounter in using wireless audio. So let's look at the transmitter end. Um, Wireless mics are usually of two physical types. There's a handheld, and there's the body or belt pack. Usually has a lavalier mic on capsule on a cable connected to it. But despite the physical difference, they both really work the same way. Of course, we use a mic to convert sound into an electrical signal that goes into the mixer or whatever the system is. So even with a wireless mic, it still starts with a mic element. We're not going to go into the different types of mic elements because there's dynamic and as well as uh, condenser, electric condenser elements and different patterns and stuff like that. We'll just leave it at it's a mic element. It converts sound into an electrical signal. Now, in the wireless mic transmitter, if it's a digital transmitter, it's going to go into an analog to digital converter first, and depending on the type, that might produce like a digital stream. In the case of like digital hybrids mics, like the some of the electrosonics model lines, they could also convert into a fully digital modulation of the FM transmitter, and that's more along the lines of like the fully digital systems by like Shure, Sennheiser, Electrosonics, and others. So the if it's an analog mic, there's no ADC. It just goes directly into the FM transmitter and modulates that carrier into an FM carrier. Now, an analog wireless, the stronger or louder the audio is, the wider the spread of frequencies. Now, this deviation, this variation from the center frequency is called deviation. So the louder or stronger the audio signal is, the greater the deviation will be. It'll be swinging, to a higher frequency and to a lower frequency and back and forth, according to the audio signal. Now, in most applications, the typical maximum deviation may run up to about plus or minus 75 kilohertz. That's common in some of the electrosonics models. Sennheiser is usually, the RMS maximum deviation often is like plus or minus 40 kilohertz, meaning the peak deviation will be about 50 plus or minus 56 kilohertz. That can vary though from brand to brand and model to model. And in some countries, the amount of deviation is controlled, so they can only do maybe plus or minus 15 kilohertz or something like that. So the signal itself is called the carrier. The information that's encoded or modulated onto it is called the intelligence. Now, that's just a technical term. It's objective, it's technical. It's not a judgment of the quality of the information or the aesthetics or logical assessment of the material being conveyed. It could be somebody saying the stupidest thing on earth. It's still called intelligence. So let's see. The RF carrier signal goes out from the transmitter circuitry into a little antenna. Now, they're little, fortunately, because we're using UHF frequencies that have inherently short wavelengths. Body or belt pack transmitters usually have a whip antenna made of wire, although some actually couple the RF onto the lav mic cable and use the cable as an antenna. Handheld ones may have a visible whip or an hidden internal whip and whip antenna, or they might have some other internal type like a coiled whip. So the antenna couples the RF energy into surrounding space. Mic antennas are not directional, so the RF just goes out in all directions. So in that space, the RF energy may encounter surfaces or materials that reflect radio waves, or maybe absorb them, or just pass them through. In general, it's a good practice to not have any obstacles between any obstacles that absorb or reflect RF in between the transmitter and the receiving antennas. Now, you need a clear line of sight. Now, a visual line of sight, that you can see with your own eyes, is always good. But there may be times in film or TV production when you have to pick up through components of a set, like we see here on the left photo there. Now, those are two antennas up here. Those are two RFNU CP beam antennas aiming through the plywood, the Luan and 1x3 wood of a movie set. Now, wood passes RF really well. Glass does, plasterboard. These things pass signals really well. So you can do this, even though it's not a visual line of sight. You still have essentially an RF line of sight. So on the right here, we have a visual line of sight. This production sound mixer has the antenna, the diversity fin, way up on top of a mast in order to get a direct line of sight, a visual line of sight to the transmitters that are often in the distance. So the receiving end is where the radio signal will get picked up and converted back to audio. Professional grade analog systems use diversity reception, which employs two antennas and receivers that select audio from the two antennas and RF stages, I should say. And the receiver selects audio from the antenna input that has a stronger, higher quality RF signal. Now, diversity provides mutual redundancy so that you never see a dropout unless there just happens to be a bad signal on or no signal on both antennas simultaneously. If one antenna has a good signal, you're good to go. If the other antenna has a good signal, you're good to go. Most of the time, you'll have a good signal on both. So it's very rare but not impossible, to get a dropout on both antennas at the same time. Multi-channel systems will use a distribution system or distro that is essentially a dual distribution amp for RF that splits the two input signals from the antennas and sends them out to multiple pairs of outputs to feed your multiple receivers. Now, most digital systems also use diversity, but in possibly varying ways. Now, there are a growing number of ways that digital systems work and use diversity. But the same idea is there, that you have mutual redundancy, so that if you do lose signal on one antenna, there's the other antenna there. And if that antenna loses something, the first antenna is there. So that's diversity. So let's say statistically, one antenna gets a fine signal 99% of the time. Now that might sound good, but that also means in every hour of the performance, you're going to get 36 seconds of dropouts on that antenna. So that's why you need that second antenna, because maybe it is also 99% reliable, and hopefully it'll pick up 99% of what the first antenna doesn't get, and vice versa. So technically, actually more theoretically, you could possibly get, with that setup, 99.99% reliability, and that's just then that's less than a few milliseconds, or 360 milliseconds possibly of dropouts per hour, potentially. Okay, so this is yeah, like I said, this is diversity reception, two radios and one receiver, and mutual redundancy. So um, the best design goal for receiving is to use one diversity pair of antennas, unless you have multiple zones to cover with the same system. But that's a topic for another time. We'll talk about just one diversity pair, and you use a distro, as we mentioned in the previous slide, to split that out into your multiple receivers. Definitely don't do what's on the left here. This is what we call an antenna farm. When you have a whole bunch of antennas just tangled together, all close together, that elevates the RF noise level, the noise floor that gets into all of the receivers. And what we want to do at the receivers is have a carrier to noise ratio of at least about 20 dB. So about 20 dB or more above the noise floor. But if we're bringing up the noise floor from all of these antennas that are all tangled together, that's going to be harder to achieve. So the problem is that all of these antennas close together, they pick up signals, but they also re-radiate those signals into the nearby antennas. And so you have all these antennas picking up RF, re-radiating it, that creates this cloud of RF noise around the system. So this is definitely not what to do here on the left. What you want to do is over here on the right. You have a single diversity pair of antennas, and then that goes into the antenna inputs of a distro, and then that breaks out the RF to go to the multiple receivers. Now, if you need to feed more receivers than what the distro allows, you can always add another distro and cascade it off of a pair of outputs from that first distro. And this way you can build a system that's really as big as you want. For example, our largest distro is the distro 9 HDR. That takes a pair of antenna inputs, an A and B feed, and divides that into 9 A and B feeds, 9 sets of A and B feeds to go to the receivers. You could also send those 9 pairs of outputs to 9 more distro 9s, and then you have feeds for 81 wireless mic receivers. So there's a lot of versatility there just by mixing and matching the distros in various combinations. So this is a good time also to mention bandpass filters, which can help keep out TV, mobile phone, and LED display interference out of your receiving system. Put one on each line from the antenna to the distro. So no one ever regrets bandpass filtering their wireless mic receiving systems. It's really the simplest, quickest, fastest, cheapest way to upgrade the performance of your wireless mic system. So if you see this antenna B line and the antenna A line, anywhere on there is a good place to put the bandpass filter. You can put it on the right of the inputs of the distro or right of the antenna. Either way, you're getting that effect of bandpass filtering. You're going to keep out that unwanted stuff, any unwanted RF energy that you can keep out of your active circuitry is going to be to your benefit. So an analog receiver down converts its RF signal to an intermediate frequency. So you have an FM signal that's then at a lower frequency, and then that goes into the demodulator. Typical intermediate frequencies are like 10.7 megahertz or maybe double that, 21.4 megahertz. They're popular. These are just like standard things that have been developed for FM radio for decades. If you look inside a consumer FM radio, you'll see 10.7 megahertz typically is a IF stage. So that gets demodulated back directly into audio. So we were retrieving that original audio that came out of the mic capsule. After all that RF link is being demodulated, we have the original audio back. Now a digital receiver puts the demodulated signal into a D to A converter, digital analog converter, or DAC. It could be converting a digital data stream, or it could be converting RF as digitally modulated, but its output is also the analog audio that came out of that mic capsule. So whether analog or digital, the wireless part of this haul is done. We've got our audio back. We have audio once again. So the receiver's output signals could then be used the way we would use signals from wired mic. They would go into a mixer input, or it might go into some other thing, like maybe a Dante network or whatever. We have audio again. We've got the wireless part done. So characteristics of analog versus digital. Well, analog is usually less expensive. It has zero latency because the audio is directly modulating the FM. The FM is directly demodulating back into audio. Maybe more susceptible to noise and interference. Digital systems, they have some latency because there is a finite time that it takes to sample the analog signal, convert that, measure it, convert it into data, and get that sent on its way. It's not a big problem anymore these days. Because most digital systems now have really, really short latencies, like, less than 3 milliseconds. Some singers might be more sensitive to latency. When you're talking about latency from like a digital mic to the system, then from the monitor feed from the board into a digital IEM system, and maybe they're getting a little bit of buildup of latency. Some are more sensitive to detecting that delay that they're hearing in their ears from what's going through their, bone conduction from their mouth to their ear. That's a personal preference. It's usually, most signers I think are can handle that. But just to let you know that there are some artists out there who, feel this. So digital also gives us better noise immunity, and because, like I said, with analog, the louder or more stronger the audio is, the wider the deviation. With digital, we've got a more constant amount of deviation. It's pretty constant. There's a potential for having smaller deviation, which may allow more channels to be used in the system. So let's go to in-ear monitors. So with in-ear monitors, we have the fixed transmitting antenna, fixed location, and mobile receivers that can be moving all over the place. So we start with the monitor audio feeds from the mixing board or from the monitor board, whatever. Goes into each feed goes into an IEM transmitter, which produces a UHF FM signal that carries that particular monitor mix. So you can have a large number of transmitters working in your IEM system because you have a whole bunch of different monitor mixes. It's possible also to send the same monitor mix to more than one artist on the stage if that's acceptable to them. So the design goal of any IEM system is to use only one transmitting antenna. Just like with receiving, we want to minimize the number of antennas, so we don't have antenna farms. We just want one diversity pair. With in-ear monitors, we just want to have one antenna. And so that requires an in-ear monitor combiner, like we see here on the left. We have two of them. two of our combined 6 HDR units, and utilizing the link, the passive link combiner on one of them to join um, 6 channels from one and 6 channels to the other, giving us 12 channels of feed um, to the one antenna. So this is a composite signal of all these different FM carriers going out to one antenna. The antenna doesn't care how many signals there are in the mix. It's just going to, you know, uh, beam them out to the stage. So the IEM transmitting antenna casts its signals over the stage to be picked up by the receivers worn by the performers or talent on stage. So IEM body or belt pack receivers are really too small to utilize diversity reception, although you do see some that have 2 antennas, but they're so close together and they're both oriented the same way. I can't honestly say that that is true diversity, but since we're usually not dealing with diversity receivers anyway with in-ear monitors, we have to make sure that the stage area gets a solid, robust signal of IEM um, signals wherever the performers are. So that's the purpose of using an antenna like the CP beam, which is circularly polarized directional. It's a helical antenna, so it's really popular for um, IEMs. The CP beam also is popular too. It has a wider pattern though, but the circularly polarized signal will be picked up in the receiver no matter how it's oriented. And you don't get that with like single polarized antennas like paddles or whips. But other than that, IEM transmitters and receivers work very much like their mic counterparts. So we don't have to go back and go through, the modulation and the demodulation and all that. It's really just the same thing in the other direction. So now we're going to get to what I call side stories. These are just little tidbits that give you a little illumination of the whole system. Um, Now, first, I'm going to go into the little messages that mic transmitters send to their receivers. Not all of them do, but some of them do, and it can really help you out when you're operating a wireless mic system. First is squelch tone, also known as the pilot tone, something. Uh, this replaces the squelch adjustment used in some older receiver technologies. If you remember, if you've used older wireless mic receivers or even some of the current ones, there's a squelch knob, or maybe there's like an up and down, like you select different squelch values, and what you do is with the transmitter turned off and the receiver just listening to dead air, you just advance the squelch adjustment up until it mutes. And then the idea is that when the transmitter is turned on, then the receiver will open up and pass audio. It's kind of like a noise gate for audio, but we're using RF. So the squelch tone replaces that squelch adjustment, and it's a tone encoded on to the FM signal at the transmitter. And when the receiver detects that tone, it knows, oh, my signal is here. Let's open up for business, and pass the signal through. If the tone isn't there, it mutes the audio and prevents noise, and also prevents picking up maybe some other signals that might happen to hit that frequency. Uh, Battery level, that's another good one. That saved my skin a couple times in doing theater shows, especially in like rehearsals and stuff like that, where you're using batteries that have already gone through 1 or 2 cycles. We always use fresh batteries for shows, though. But it allows the receiver to display the transmitter's remaining battery capacity as a bar graph. And that can help prevent disasters of having a battery run flat during a performance. Now, these can be misleading, though, because they're usually calibrated for whatever type of battery the manufacturer specs, like perhaps alkaline cells. You know, a full alkaline cell puts out a voltage of usually around 1.6 or so volts. And so when you have two or three or four of them in a transmitter, you're reading that voltage, and that's what the display is calibrated to. Now, if you use rechargeable batteries, which is often a very valid choice to do, a lot of them have a fully charged voltage that is different from the alkaline cells. And so they might be starting off at a lower voltage. And so you might see a lower value on the battery bar graph. So even if the rechargeable battery has a larger capacity than those alkaline cells, it's still going to might be a little bit unnerving to see the show starting off and you're already only at it makes it look like it's at 2/3 of the full capacity. Well, that's just something you have to understand and maybe, work out how long those rechargeable batteries actually last on a full charge. So that's something that you might have to experiment with. Mute. A lot of receivers and have a mute display that will be triggered by the mute switch on the transmitter. That has saved me also when I'm setting up for a show, because sometimes when you hand a body pack transmitter to an actor, they're putting it on and they inadvertently hit the mute switch. I usually tape them to with gaff tape to keep them from moving, but sometimes accidents happen, and the actor accidentally mutes his or her transmitter. So you see that on the receiver, okay, we have to tend to that, and warn the actor, please be careful when you're putting this in your belt or somewhere in your costume. So this this need is obvious. It really helps you sometimes. Audio levels. This is really good. It's good to see what the audio level is in the transmitter, because if you're not getting it at the receiver, there's something wrong in the system. It knows that, okay, the transmitter has audio. Why isn't it coming out of the receiver? It gives you a little bit of insight into what to troubleshoot. So these indications can be very useful for a sound engineer, and will help him or her live life to the fullest. Another side story: coaxial cables. This is a topic that we often get questions on. So at the fixed end of the wireless audio system, whether it's mics or in-ear monitors, we use coaxial cables to connect among antennas, distros, transmitters, combiners, receivers, etc. Always use 50 ohm cable. Don't use 75 ohm cable, because that's for TV and video systems, CCTV, cable TV, so on. It will not work well for wireless RF systems because you'll have an impedance mismatch that will cause reflections and uneven frequency response, stuff like that. So use good quality 50 ohm cable. At RF Venue, we sell RG8X. That's a really good combination of performance versus price. It's a nice meeting point. RG8X also that we sell is double shielded. And I'll get into the importance of double shielding in just a minute. But anyway, it's called coaxial cable because the inner and outer conductors share an axis, okay, along the length of the cable. The cable keeps out electromagnetic interference, and it doesn't create electromagnetic interference from the signal carried inside. And that's because of this coaxial geometry. The electrical field, radio waves are electrical and magnetic fields together. So you can't have one without the other and still have it be a radio wave. So the electrical field is fully contained between these two conductors. The magnetic field also, because these two conductors running along one inside the other are essentially, in a magnetic way, they're essentially occupying the same line through space. So there's no loop area. You need to have some separation between the conductors in order to have a magnetic field develop between them. So if they're really, if one's inside the other, they're occupying the same line through space. So you're not going to get an electrical, you're not going to produce a magnetic field, and it's not going to pick up a magnetic field either. So the construction of the outer conductor or shield is important because it has to surround the inner conductor completely. It has to completely encircle, no gaps or anything, and it also has to have low resistance. Now, foil shielding gives you complete encirclement of that inner conductor, but it has high resistance. Braid shielding has very low resistance, but it can have gaps in it. And anytime you have gaps, you have a potential for not having full electromagnetic isolation from the outside. Especially when the cable is bent, you might get gaps in the braid. But double shielding with both foil and braid gives you the best of both worlds. So you have foil with braid right on top of it, and so the foil gives a completeness, the braid gives a very low resistance. So you get very good electromagnetic isolation to the outside world. Something to know about coax is that it is inherently lossy, and the attenuation increases with frequency. So here are some popular coaxial cables. There are a lot more too. There are a lot of more types. Some are better than others, but RG8X is the one that we sell for lower loss applications. So if you need to run coax a really long distance, there's LMR 400, but that's bigger and thicker, stiffer. It's more. It starts to approach the size of like a garden hose. It's less. Takes more labor to deploy. It's heavier, stiffer, and so on. EcoFlex is a good EcoFlex 10 is a good alternative to LMR 400. It has slightly better loss characteristics, but it also has a smaller diameter that's closer to like RG8X. So it's more flexible and easier to handle. But there's a price premium that you pay for those benefits. So these are things you have to keep in mind. If you have to go really long distances with coax, it might be a good time to consider doing an alternative like RF over optical fiber, which would be like our optics system 3 products. So the cool thing about RF over optical fiber is that you can go as long as 5 kilometers, and it is also flat. You don't get this high frequency roll off. It's flat across the spectrum. And so that's to your benefit. Also, side stories, things to know about antennas. Now, directional antennas are usually preferable for the fixed end of any RF link. That's because the mobile and the person carrying or wearing a mic or in-ear monitor, their antenna is omnidirectional. You're going to be moving around. Whatever they're picking up comes from all directions. Whatever they're transmitting goes in all directions. So a directional antenna allows us to point at the area of interest where the action is, and if it's a receiving antenna, it's going to be less susceptible, less sensitive to surrounding interference or whatever. And it's going to be focused in on the on the wireless mic transmitter. For in-ear monitors, directionality is good because we're essentially focusing that RF energy from the transmitters and combiner toward the in-ear monitor receivers, and that you don't need to send it out to other direction. We want it to go where the receivers are. So it's a good idea to just make efficient use of your system and go directional. There may be sometimes there are needs for an omnidirectional antenna. For example, if you need to actually put an antenna in the middle of the action, well, that's what you have to do. But usually directional is the way to go. So also, since we can't control the position of the mobile antenna, it might be some weird angle. We can't tell the singer to hold the mic upright. We can't tell them that they can't twist or turn with a body pack receiver or transmitter. So it's helpful if the fixed antenna can handle all possible polarization angles. And this was really why our antennas are kind of funny looking, because we design our antennas to pick up or transmit in all possible polarization angles of the RF signal. So that's something to keep in mind also when you're selecting antennas. And lastly, I actually get phone calls from people who, they set up an IEM transmitter or transmitting antenna on one side of the stage and put their wireless mic antenna on the other side of the stage and aim them across. Don't point your IEM antenna at your mic antenna. Just don't. Put them on the same side, or if you have one in front of house and one on the side of the stage, okay, that's fine, but don't point them at each other. If you have them on both sides, both on the same side of the stage or at front of house, separate them by 5 or 6 feet or so. It's often good to have the receiving antenna maybe a little bit back of the transmitting antenna, but that's an important thing because you don't want to be pushing IEM RF energy, because I want a good, powerful, strong signal. We don't want that going into the wireless mic receiving antenna, though. That's, like I said, the more unwanted stuff you keep out of your wireless mic receiving system, the better off you are. Okay, so we're at the end here. Any questions? Let's see, the singer has a question.
Absolutely,
But
Bob. We've got more questions than we have time for.
all right,
So we'll
that's what I
start
like.
that. You guys have submitted lots and lots of questions. But first, I'm going to send in the chat a feedback survey to give us your feedback about this webinar, future webinars, any topics you'd like us to see. Definitely let us know how we did. Make sure you give us that feedback because we always like to improve. But let's go ahead and kick off the first questions here. And also, just so you know, we're going to try to answer a lot of these questions you submitted directly with you. There's a lot going on here, so we'll interface with you one-to-one if your question isn't answered. And thanks, Richard, for answering all the questions that came through the Q&A. There's a lot going on there. I hope everybody learned from those. But let's start with the top here. What recent design and implementation challenges were you able to overcome by utilizing RFNU solutions?
You want to go first, Bob? Or
No, you go,
can
Rich.
trip it up? So again, the question is, what challenges have you overcome by using our items? Is that basically what it's saying?
Yep. So what recent
Yeah.
design and implementation challenges were you able to overcome by utilizing RFNU?
Okay, so it always starts with you're battling noise. So if we can do that with the right antenna, the right cables, the right distro, and then we have spectrum tools that help us find the noise. It's all a complete package that we offer. And designs can be pretty small to pretty large. The more antennas you put up, the trickier it is. So just remember that even the most simplest system with 2 antennas for AB diversity, if you don't avoid noise, you're going to get into trouble fast. So consider a spectrum analyzer if you haven't had one yet.
Excellent. Next one. This is probably my favorite question that I've ever received at this company. Why is there so much wire in a wireless system?
Yeah, that's a kind of a necessary thing. Although it's if you can minimize the amount of wire, that's good. Sometimes, I've done a lot of theater sound over the decades, and sometimes I've seen it, especially in like historic theaters. They have a pair of antennas mounted on like maybe a cross beam or something up above, and they send the cables, from the antennas out to the sidewalls, and then it has to go around columns and other architectural features and stuff like that, and then ultimately to the receiver rack at front of house. Well, there's a lot of roundabout routing in that cabling. If they had just moved the antennas maybe 15 or 20 feet back, they might have saved 50 feet of coax cable. Or if, I don't think the front of house position was a bad location. They could have put the antennas there at the front of house and just had really short cables, like 5-foot cables, and that would have saved a lot of loss of signal in those coaxial cables. So really, sometimes you can just plan the system differently and use less cable.
I have something to add too. So in regular wired audio, you have balanced cables. You should compare double shielded RF cables to balanced cable, even though it's not the same circuit. It's the bare minimum you should go for. You wouldn't run a microphone on an unbalanced signal long anyway. So you have to get the right coax cable.
Awesome. Yeah, great question. Thank you for that. So here's
Well,
the
I'll
next one.
I'll add something to that. Sometimes just locating the receivers. If you got a really difficult situation where you have it's just this really long distance to the stage or something like that. Sometimes it might be better to locate the receivers closer to the antennas, wherever you happen to put them, and run longer audio cables because good balanced audio lines are fairly low loss compared to RF coax cables. So sometimes that's a better answer, or even use like a media network like Dante or QLAN or something like that to send the audio a longer distance.
Yeah, absolutely, Bob. We're seeing a lot of installers go the Dante route where they much prefer to run 25-foot BNC cables from a remote antenna and lots of length from a Dante network. So
Yeah,
locating the receiver near the antenna and then having full complete control through the building with Dante. So
yeah.
very cool. All right, this is a really good one. I'm sure everybody wants to know this. Sennheiser and Shure both released high-density wireless products. How is this technology different from previous digital wireless?
Oh, that's a topic for a whole session itself, really. Uh,
Yeah.
they're doing a lot of like sort of like interleaving of carrier frequencies and stuff like that. Uh, they're really good for like using just a whole block of channels in a 6 or 8 megahertz block of frequencies. Um, I we're still really exploring how we can you know how we can benefit the users of like WMAS and stuff. Um, I think Shure is maybe offering some flexibility in that regard, that where you could use RF venue products for sort of more customized antenna situations. Rich, do you want to
So
add
yeah, so
something?
so overall, yes, if you're curious about WMAS, you should do the research because it's apples to oranges. And that is Shure is using 800 kilohertz wide carriers. Sennheiser's doing
Mhm.
six in the US, 6 megahertz, and 8 megahertz in Europe. But it's both of it is basically multiplexing. It's combining sub carriers within one big carrier. So you have to realize that it is more spectrally efficient. It is going to change your way of doing your distros and things, but it's not going to. The thing is, you have to remember that the traditional 200 kilohertz systems that are out now are going to stay. People are going to need that. Not everyone's going to have a WMS product. Just like with intercoms, you have the digital ones or the ones that operate in 1.9, and you have analog ones that wired on the wired side. So it covers think of the two types of transmitters now we have are 200 kilohertz and WMAS. They're both going to be needed.
Excellent answers, guys. I think as the technology unfurls, we'll have a lot more info. I know the guys are planning on doing some blog posts about WMAS soon, so keep an eye on the RF Venue blog for more info on that. Now, this is the age-old question, pretty general. You've covered a lot of it already, but let's dive into it. How to avoid dropouts?
That's another webinar topic. I think we've covered it in some webinars or whatever, at least in.
Well, how about this? Why don't you
part.
guys both give us the top 3 points that you want to look at when you have dropouts? What would you do?
Okay, little advice that I've learned from like Jim Stoffo. He's a well-known RF coordinator. BC, antennas, batteries, coordination. Okay, those are 3 ultra important things to take care of in a wireless audio system. Coordination is always job 1 when you're planning a multi-channel system, or even just a system that has to coexist inside of in an area where there are TV stations or maybe other wireless services, maybe intercoms and things like that. You have to coordinate your frequencies just to make sure that they're compatible with each other and also compatible with the RF environment. Batteries, okay, that's self-explanatory. Antennas, you got to have good antennas. That's, like I said, RF Venue has funny-looking antennas, but they're that way for a reason, because we're addressing things that a lot of manufacturers haven't thought to address. So we're addressing issues of polarization, because when you have the polarization of the signal from the transmitter and it happens to be at a 90-degree angle from the single polarized antenna, you're not going to have very good coupling of the signal into that antenna. So we address those things. So, if you take care of that, and also, if you have a spectrum analyzer and you can check, the RF noise in the environment, you can get that 20 dB of carrier to noise ratio in the receiver and have just a really solid reception.
Cool. You want me to continue?
Yeah, Rich, give us your top 3.
Yeah, so basically you have to avoid noise, and the biggest one is TV. If you don't know if you're on either low power or high power TV station, you have to know. You use a coordination program like our System Builder or Workbench or Soundbase to enter an address, and you figure out where you are versus the database of what's on air. You use a spectrum analyzer to figure out if you're off of a TV. So get off TV. Use your gear right. Point the antennas right. Use good cables. Pretend your antenna is like a microphone. You got to point it in the right direction. You got to follow signal all the way through, and make sure that the signal is not lossy, and keep it strong all the way through your system. And then finally, yes, coordinate. You can be creating problems by your coordination being poor, and that's noise. Poor coordination causes noise. So all 3 points I just hit, if you don't do it right, you're going to cause noise, and noise is their enemy.
Awesome. Well, it looks like we only have time. We've gone a little bit over our time. Thank you all for sticking with us today. Let's answer one more. Let's see here. So what is the best gain structuring practices for antennas and cable?
Well,
yeah, go ahead.
I always think of gain structuring as being more something that you put you do on your board, on your mixing console. With wireless mics, if you're talking about gain structuring of like, what sensitivity is set on the transmitter, that I would go by what the manufacturer recommends, because sometimes you'll need to boost the sensitivity of the mic going into the transmitter, or sometimes cut it back depending on the whoever's using that mic. Um, the the RF gain is really something that you're going to have to, deal with. There's really not much to adjust there. You just have to use suitable antennas, aim them in the right direction, and so that they're most sensitive where they need to be picked up, and so on. So
Yeah,
that's
so
my
yeah, cool. Just remember your antennas can make up gain. Your cables, you can lose gain. So you do the math from the very beginning. Antenna in, you look at the gain spec of an antenna, you look at your cable loss, and then you figure out what's hitting the receiver. So you don't want loss. You want everything to be as even as possible. So think of it that way.
Awesome. And we just got one last one here because it's related to that question. So
okay.
I'm gonna give this to Richard because I know he knows this one. To piggyback on the gain structure question, what should I use to gauge whether or not my RF gain is hot enough without overload?
So if you look at the receiver looks for a signal lower than 0 dBm, basically. It's just a rough math. It'll detect something too strong. And if you look at a spectrum analyzer, your signal will be below 0 dBm. So if you don't have a spectrum analyzer, the receiver will tell you if you're overloading. So the perfect example is put a transmitter right up to the receiver and you'll see it go into that meter mode. When your transmitter is far away, sometimes it still may overload based on its reaction to the room. I've had it where a transmitter was out 100 feet away from the antenna and still overloaded the receiver.
Wow.
So you
Great.
never know.
Yeah,
Go ahead.
I like to add something. A lot of people just assume, in advance that they're going to need an active antenna or that they're going to need inline amplification. I regard those as last resorts because they usually add more problems than they solve if you don't have a specific problem to solve with that. So, and an active antenna can be overloaded by a strong signal. A passive antenna can't. An inline amplifier can be overloaded by a strong signal, but just cable can't. So if you don't overload your active circuitry, you're not going to you're going to eliminate a lot of possible intermodulation problems. So just don't don't use amplification injudiciously. Be be really sparing about it if at all.
Great answers, guys. And one thing I've picked up from all of you guys and all the top RF guys that I talk to daily is that they generally prefer padding their antennas down. I guess radios just seem to work better with less signal. You're jamming all this complicated information into a radio receiver. It doesn't understand the difference between the noise and the signal, right? So having more intelligible signal allows the receiver to just work more efficiently. Would you guys agree with that?
Yeah,
Yes.
yeah, that's often the case.
Awesome.
Because
Well,
usually you're dealing with a strong enough signal anyway, and less often with a weak signal.
yeah, it's kind of counterintuitive to audio people who generally like to get to full scale digital audio and
Yeah,
get as loud as you can before feedback and whatnot. But this is a whole different idea, playing on the same principle, signal to noise ratio. So understand your dynamic range, understand your signal strength, understand your interference, and keep going towards that 20 dB golden rule, as I'll put. So
Yep.
Thanks everyone for your time. That's all we have for today. We went over and you hung with us. I really appreciate it. As soon as this recording is processed, I'm going to go ahead and send that to you guys, all who registered. So I realize there's a lot of information in this presentation, so we'll get that over to you so you can review whenever you have time. So thanks again, appreciate it, and looking forward to seeing you on the next webinar.
Thanks very much, everyone.
You guys.
Thanks, guys. Take care.